something, and maybe you're already full, and you'll get nothing out of my talk, but then it's only an hour, so it will be okay. Yes, so I have worked a lot on variation autoencoders, also hierarchical variation autoencoders, and once the diffusion models came on the scene, of course, because I was very biased, I thought, you know, this is just a specific instance of a variational autoencoders with some very nice properties. I'll come back to that. But I also noticed that, especially with the variational diffusion model paper from Kingma and others, that in the end you can take this limit of the number of layers to infinity, and then you get something that is well defined. And I couldn't understand that. So I was kind of felt like, okay, I need to be a postdoc again to have the time to sit down and actually kind of understand how this works. And I know a lot of you have probably learned about Fokker-Planck equations and that kind of stuff in school and understand it perfectly. Maybe I also learned it in school, but it's so many years ago, so I forgot maybe the lecture where we had about Fokker-Planck equations. So I kind of became, during this spring, a postdoc again and went back and really, you know, dig into kind of the sources of the Fokker-Planck equation and the connection to stochastic differential equations and other things. And I think it was worthwhile, for me at least, but now I will communicate some of the results from my investigation to you. That's kind of my goal for the next hour. So I'll start out kind of recapping a little bit what you have seen today with variation autoencoders and hierarchical versions of that and how we can kind of move that to the diffusion models. Then I will move on to the Fokker-Planck equation, which you can think about as like a master equation for everything we do with diffusion models where we take the number of layers to infinity. So it is really like kind of the kind of foundation of everything we do. And I think kind of my frustration with reading a lot of these kind of diffusion papers from Song and other really good researchers is that they kind of always just say, and then we take, you know, this equation, and it's like, I didn't know where it came from, so that was like kind of got me frustrated, but also like, so, okay, here's actually a chance to learn something new. I will also talk about the stochastic differential equation, ordinary differential equations, and also the reverse time stochastic differential equation. So that's kind of a stochastic differential equation where we run backwards in time. And that's a very famous result. I will come back to that, where you can actually kind of translate between these. And then I will kind of go back and look at essentially like the variational diffusion model again, but then now treat it as an ODE on SDE. And this is what I'm going to talk about here is based on a paper that we are currently working on. Currently with this set of authors, I don't know if maybe there'll be more authors in the end. Depends on where it goes. Yes, so I don't know, I have a few kind of really introductory slides. Maybe it's kind of wasted on you guys because now you're experts. This is kind of the famous figure from the OpenAI blog before they made GPT, where they kind of nicely describe kind of the power of having a latent variable model. So you start from some space, the latent space C, and then you have some transformation. So you can take a simple distribution and you can mold that into a distribution that fits with kind of the true distribution of your data, which is kind of shown in the blue on the right. So you can formally write that as you have that if you want to go probabilistic. Now this is probabilistic AI, so this will be a super probabilistic talk. You'll don't want any more probability after this talk. I can tell you that. You'll run out screaming. No, I think calculus is really your friend when you deal with these things. Yes, so you can think about this as you have a latent variable C that you draw from a simple prior distribution, for example, a Gaussian distribution, and then you have a very complicated transformation that takes that into kind of into the observation space, or kind of provides a distribution for the observation. So if the observations are like kind of multinomial, so kind of discrete, then you can imagine that actually you transform the C into logits, and that will give you the probabilities for the different outcomes for X. And no shit, what happened here? I don't know. I hope it's, oh no, I just need to do escape and full screen again. Hope that will enter full screen. Yes, it worked. Technology is my friend today. Yes, so of course, as you also know from today, C is what we call a nuisance parameter, so we need to integrate it out. It's our friend because, you know, we can model complicated distributions with simple distributions, but it's not our friend because we also have to get rid of it because we don't know what it is. When we don't know what it is and we are probabilistic, we integrate it out. So this kind of integral is kind of something you can spend your career on trying to find different approximations to do that. Have you seen this slide before? Yes, it's beautiful. It's Yes who made it. I just wanted to, always when I talk about VEs, I will have to show his slide. So, so we need to integrate out the latent variable, and this nice invention in the VAE is that you introduce another distribution, a variational distribution, and then you use that to actually kind of map from the data to the latent. And it's not an autoencoder really, because you actually do it in a way where everything is okay, meaning that you can actually, you cannot overfit this variational distribution, this Q of C given X, right? That you actually have this log likelihood bound, and you want to make that as tight as possible by choosing your variational distribution in the best possible way. And what is special about kind of the VAE is we do what we call amortized inference. So we learn a mapping from X, from any X to any C, right? And that will be shared across the entire data set. We could also learn a distribution for each and every data point X, but that's kind of a waste of resources. So kind of one of our first papers into this game of variational autoencoders was back now 8 years when one of my PhD student Kasper he looked at like how would you do a hierarchical version of a VAE, right? Because you can think about, okay, you can actually stack these latent variables, and probably if you had some kind of phenomena that actually lived on kind of multiple hierarchies, then you could get a better model, right? You can think about if it's the CELEB A database, then you could maybe say in the highest layers of the latent, you could have something that encoded like the overall pose, and then when you kind of work your way through the hierarchy closer to the data, you can put on more details. So it makes sense to build these kind of hierarchical latent variable models. And the first ones on the market kind of worked in the way that you kind of reverse the error. So the kind of direction of the kind of the generative model goes from like high indexes towards low indexes, and then you would kind of in the variational distribution go the other way. And kind of what Kasper invented was inspired by what was kind of popular at the time called the ladder network, where we kind of reversed the direction. So we had this kind of deterministic mapping in the variation. We made the variational distribution more advanced, but we had this kind of deterministic mapping where we kind of send some signal through some layers, and then we kind of get, you know, Q of C2 given X, and then you could actually kind of go the other way, so that actually C1 is conditioned both on X and C2, and then actually you could introduce parameter sharing between the generative model, which you can think about as a prior, and then like this kind of other thing that you can think about as kind of things coming from your data. And that also worked. I mean, you could get some improvements over kind of models with only one layer, so that was really nice. And and pretty nice piece of work. Then we move to the diffusion models. And there you can see the idea is somewhat similar, but in a way what we kind of spent a lot of time on when we did these latter VAEs was to build very kind of tailored architectures. So typically we would start out with, in the first latent layers that we had many latent variables, and then you moved up the hierarchy, you had fewer latent variables, because you say these kind of high-level features like the pose and so on, you only need few latent dimensions to represent those. But that's not what we do in the diffusion models. There we simply say, okay, if we have an image which is like h by h by c, then our latent variables will have the same dimension, or more or less. You can also kind of change the dimensions and then run your kind of latent diffusion in another dimension. But like, let's just think about it as we kind of preserve the number of dimensions, right? So there's not, we kind of throw away all these kind of ideas about spatial structure in the hierarchy. Also, another thing we do is that, another thing that we spend a lot of time on when we build these kind of ladder variational autoencoders was we made very advanced models here. They were like the neural networks of more or less the same size as the generative model. But in the DDPM world, we make the encoder very, very simple. So for example, if you look at the marginal distribution of the variational distribution, so actually we integrate out, let's look at like layer T, we integrate out everything in the latent dimension, latent variables apart from layer T. Then we approximate that just with a normal distribution where the mean value is just the original data scaled with some factor alpha, and then we have add some noise. So that's what is illustrated here, right? That the kind of diffusion, this is kind of, you can think about that as a diffusion process. So you start with the data, and when you move your way up the hierarchy, you add more and more noise. So in the end, when you get to the top of the hierarchy level, layer T, then all information about the data is kind of removed. And that also makes sense because if you think about the reverse process, the generative process, then kind of we start out here with a simple prior, which is just kind of IID Gaussian noise. So that's one invention compared to the VAE. Another invention that I really like compared to the VAE is that we use parameter sharing. So that means that each of the layers, each of the transformations in this hierarchy use the same parameters. Of course, we need to be able to distinguish between the different layers, because probably when we kind of get closer to the data, we add more details, right? So we need to represent higher frequency components, and closer to the prior, we need something else. So we managed that by having that the mean function of this conditional in the generative depends also on the layer index, right? So we can actually learn, the model can by itself kind of learn to kind of act as a filter. So you can imagine this as kind of like a learned high pass, low pass filter, something like that, right? And I think these two inventions are really nice, but from my old biased mind, then it's a variational autoencoder with these particular properties. Okay, so now the next thing I want to do is I want to talk a little bit more about the VDM, and also like what you can do to make the VDM closer to a variational autoencoder, right? Remember I said that we spend a lot of time trying to build very advanced encoders, and that's been thrown out with the kind of diffusion approach. Can we actually introduce more complexity in the encoder? And the idea now is that we have this log likelihood lower bound, and if the encoder is better, then we can make that tighter, and then we can learn a better model, right? So that's kind of the idea. So in the VDM is essentially, have you talked about that today? No? Okay. So the variational diffusion model is essentially the same as the original diffusion model. It's just, you can say, a little bit simpler notation. And it's simpler notation and also in the way that it makes it easier to take this limit of infinite amount of layers. We start with the same model as we had in the DDPM, right? So we start with, we have a prior distribution at index 1. So now our indices are not like 1, 2, 3 up to t. They are like fractions, and we'll see later on when we take the continuous limit, it's nice to have fractions. So you just remember that the prior is at index 1, and kind of the latent variable that connects to the data. So the likelihood term has index 0, and then all the layers in between, they are like evenly distributed on the interval between these two. But it's just this model here, right? That you start here and then you go towards the data. Then you can write down the elbow, the evidence lower bound, or the log likelihood lower bound. And yeah, I wrote down, let me just repeat it. This is just this term, but now we have C is, you know, T plus 1 layers. So it gets 3 terms. It gets a term we call the reconstruction term, because that's like, it's like the expected log likelihood. It has a prior term, which is a KL divergence between the prior, which is this kind of 0, 1 normal, and then our encoding of the corresponding latent variables. And then it has a diffusion term, which is just a KL between all the intermediate conditional distributions, and then it's averaged over this marginal distribution here. And what we then do in the VDM model and also in the DDPM model, probably you have done that exercise today or seen it on the blackboard, is that we take the diffusion model kind of going from data towards the prior, and we then reverse the directions using Bayes' theorem, right? Sounds familiar for anyone? Or is it new? The teacher knows. Okay, yes. But that's like, yeah. And kind of, you can see that actually the way we have defined the variational distribution kind of going from data to prior, we have these conditionals here that does not depend on the data, but when we reverse the direction, because everything is connected to the data through the first term, then all these new conditionals will depend on the data, right? So if you look here at the KL, it's KL between this conditional. Now they're both going in the generative direction, but you can see that the variational distribution depends on X, right? And I even gave kind of the marginal distribution here also depends on X, right, in that way. Yes. Yes, and then you can kind of sit down and do this exercise. It's horrible, several pages of, you know, completing the square. But then in the end, you get a very simple expression that you have this conditional distribution has a mean that depends on CT and X, and then it has a variance that only depends on like kind of the variances in a simple way. And you can also choose, because now we have to define the generative model, so you can also choose actually the generative model to have the same shape. Of course, this mu p cannot depend on X, right? Because it's a generative model, so it can only depend on the previous latent variable. Then, as a choice, you can choose to actually use the same. So this mu p, you are free to choose that, right, in your generative model, but you can choose that it has the same functional form as your variational distribution. Then instead of X, you have this kind of X hat, which now cannot depend on X. It will depend on then on CT and T, right? And this is kind of where your neural network comes in. Yes. But now you can see we have these 3 terms. These 2, as you can see, are Gaussian distributions. So that actually means that you can calculate this KL divergence exactly, and it becomes this. Just believe me, it's another horrible long kind of trivial calculation. And you can see now that it depends on, as kind of a weighting factor in front of all these t terms, it depends on the change in the signal to noise ratio. I didn't define that, but I had it on the previous slide, so let me just go back. So the signal to noise ratio is this quantity, so it's kind of this coefficient in front of x squared divided by the noise square, the kind of the noise variance. And you can see close to data, so out here, then alpha will be close to 1, and sigma will be close to 0. So there the signal to noise ratio is infinite. And then when we go over here, it becomes 0 because this alpha goes to 0. And these are kind of the signal to noise ratio, and as a function of t, of the index, of the layer index, is something we can choose. It's just a parameter we set. And if you look in literature, different people define it in different ways. But let's go back to the results. You can see we have this delta signal to noise ratio that already kind of tastes a little bit of a derivative, right? Because it's kind of, if the layers are, so to speak, close, then this difference becomes small, so this would be closer to a derivative. So we can now try to take the t going to infinite limit, and we can do that by dividing by delta t. So delta t is just kind of the difference in index between two adjacent layers, which is 1 over t, and then we multiply by t as well, right? You can see there's no delta t in this expression, so I divide by delta t and multiply by delta t, and now I take the t going to infinite limit. I'm not a mathematician, sorry, but I believe that the limit, that it's well defined to replace these deltas with a derivative and then this delta here with an integral, right? So you replace this sum, infinite sum, with an integral between t going from 0 to 1, right? So that was also the reason why we wanted to have the indices kind of being between 0 and 1. So this is very nice, right? But it's also for me a little bit kind of peculiar that you actually started with a model with, t layers, and suddenly we have, infinite amount of layers, and we still have a well-defined limit. And I want to understand that better. You probably also learned today that, what is a diffusion model trying to do? It's trying to reconstruct the data from the latent, essentially, right? And that's kind of the objective, part of the objective. There are two other terms in the objective that we saw in the elbow slide. Okay, so what we did in an iClear paper we had earlier this year was to ask, can we make the encoder more powerful, right? So remember that in the VDM, we just put X here. Can we put a small innocent T subscript, meaning that we actually let xt be a learned function of the input and the layer index? Can that improve our kind of model? Can we get a better log likelihood? Can we get better generated images and so on? That was what we asked. And then you can play the same game as before. And what it turns out is that, of course, now instead of having that your target is kind of x here, it's kind of the encoded x, and then we also get another term. And again, this term looks really strange. It's kind of a delta x divided by a delta log SNR, right? So that means that we actually, again, can play the game of taking capital T, the number of layers, to infinity, and then we get some well-defined integral as our objective. I should also say the way in practice that you use this when you learn a diffusion model, you know that, of course, already, but that's kind of by saying, oh, this integral here, on expectation, we can replace that with just a sample uniform from t equal to going from 0 to 1, right? That's what we're going, if we're going to program this you probably sit and played with like a PyTorch implementation, you'll see there's no kind of integral here. There's just like a uniform random generator that picks a t. And then since SNR is a function of t, then you can actually evaluate this. And since also this is x hat here and x, t here, are all functions of t, right? That means that you can actually, for the sample value of t, you can actually evaluate this expression, and then you can also backprop and so on. But kind of what we did in this paper kind of left me with this kind of feeling, there's something I need to know that I don't know already, right? I would like to actually say, is there like some model that I define as something continuous? It's born continuous, and then it will give me the same results. And that's essentially what the rest of this talk is going to be about. Also because kind of my motivation is that I would always hunt for better models, right? And if I have kind of more in my toolbox to build better models, then you know, it's a higher likelihood that I'm successful with that. So I wanted to learn something new. Just to end the story, does it actually help with an encoder? And the answer is yes, but not much. So my PhD student, Beatrix, it was a little bit frustrating for her for a long time, but we actually managed in the end to kind of have SOTA on CFAR 10 for at least 20 minutes or something like that. Hard work, a lot of CO2 emitted for that. But you can see here that that we ran. I mean, Beatrix was very thorough, so she also ran the VDM. So we essentially took the VDM model, which was kind of close to the SOTA model for a long time, and then we just ran it exactly with the same size network and so on, but just with this learned encoder. And this learned encoder was kind of like a smaller version of the UNets you use in the generative model. And you can see that we get like we go from 2.64 bits per dimension down to 2.62, and then other people have beaten us after that. Sorry, but that's how it goes. That's science. What does the encoder learn? And here you can see we visualize the encoder for different values of t. So remember, t equals to 1 corresponds to the prior, and lower t corresponds to something that is closer to the data. So it seems to me, at least, that it kind of learns, it kind of encodes the objects in the image, right? Yes. Okay. Motivation is over, but now the new stuff starts. Yes. So just to set the stage. And here, I mean, from now on, really encourage you to ask questions if there's anything that you don't understand. If it's too strange, probably 20 other people thinks it's strange as well, so it's fine to ask. Yes. So what I want to do is I want to kind of be able to kind of take these kind of generative models and then formulate them directly with kind of in a continuous setting. And luckily, I'm not starting from scratch. A lot of people have been working on this. Maybe like Song is the most famous one in this game. Yes. And I'll just change the notation now. This is really bad, but it's just because it's different notation we use in the paper. So now I call the stochastic variable x, and I also write kind of the time dependence like this. Right, so it's a stochastic variable, and I'll do everything in 1D just to make the notation simple. So it's a one-dimensional stochastic variable that is defined over an interval between 0 and 1. I'll call now the data y. Time is going between 0 and 1. Time equals to 0 corresponds to the prior, and time equals to 1 corresponds to the data. That's because I think about it like a generative model, right? You start at time equals 0, just generate some noise, and then you run the process, and then you have data, right? So that's, but it's the opposite kind of time way of treating time as in the DDPM. I'm sorry about that. You are all very intelligent people, so you can change that direction in your head on the fly. So so a good way to think about kind of stochastic variables that change over time is a stochastic variable that follows some kind of differential equation, right? So for example, you can have a stochastic variable that changes over time according to an ordinary differential equation. And then you can say, okay, but it's not stochastic. Yes, it is, because at time equals 0, you draw from that distribution. And that, of course, means that all the following times you also have a distribution. But it could also be that that you have a stochastic differential equation. I'll come back to what that means, but you can just think about it like this, that you have some kind of term like in the ordinary differential equation, and like a drift term, and then you have dw, which corresponds to noise you add to the stochastic variable. You can also have an interpolant where you actually have two kind of anchor points at time equal to 0 and 1, and then you interpolate between the two. And if y1, for example, comes from a distribution, then also x will come from a distribution. It turns out actually that all these examples I mentioned here, kind of, they follow the same kind of master equation, or rather their marginal distribution follows the same master equation. That master equation is called the Fokker-Planck equation. It's also called the Kolmogorov forward equation. So what is the marginal and how do I denote it? So I changed the notation as well here, so that I write the marginal as like p of x, sometimes with index t, comma t. But it's very important to kind of remember here that t is a parameter and x is a stochastic variable. It's just to kind of highlight that this marginal distribution has an explicit time dependence. And it also has like an implicit time dependence because x depends on time, right? So here's an example of this. So kind of time runs from 0 to 1, and then you can see how this kind of marginal, I kind of plot the marginal distribution for 5 different times. You can see how this marginal distribution evolves over time. And what I will kind of teach you is kind of what is the equation that kind of governs this kind of moving over time, and how does that relate to how we define, for example, an ODE and SDE for the stochastic variable, right? So there's two things here. There's the stochastic variable, and then there's kind of the distribution of the stochastic variable. But we will learn about both. Yes. Yes, I said this already. And here is the Fokker-Planck equation. So let's spend a little bit of time understanding what goes on. So it describes the time evolution as a partial derivative of the marginal distribution, and so that's kind of the left-hand side, right? That's kind of the time derivative, the partial time derivative of the marginal distribution. On the right-hand side, there's two terms. One term where you have both of them have this kind of derivative, partial derivative with respect to the stochastic variable. And inside here you have what is called the drift coefficient V, and then you have the marginal distribution again. And then you have a second term, which is a second derivative, and then you have the diffusion coefficient again times the marginal distribution. So this is it. Yes?
Marginal distribution at time t, in the sense it would mean that if we have some time series and we observe that time series multiple times, it won't be the same, but at a particular point of time, the distribution of all the observations of whatever we saw would follow something like that.
That could be one instance, but it could also be one time series. If you have uncertainty in the time series, right, you don't know. Let's say you have a time series for that describes a patient's state. Then you have some, and this is kind of the latent variable that describes the patient. Then you have uncertainty in the patient. So you will actually have, for the patient, you have like a distribution, even for the one patient. Yes. Yeah. But you can. But I mean, I think it's great to think about different what it could be. But you could just think about it as like that T here is just, you know, an index for hierarchical latent variable model. So it's simply kind of a prototypical case in machine learning is kind of a process that shapes noise into data, right? You take white noise and then you get high resolution image of your class out as a result. Yes. Yes, okay, so there's this equation. It looks very complicated. It is very complicated in a way. I'll set that. So, of course, when I thought about this presentation, I thought, okay, I want to derive, I want to show people, you know, show the dirty underwear, show how you derive this. But then, okay, we need probably a 1 week course. But I can say that here's kind of a laundry list of how you do it. And I think it's important thing to notice here is that it's actually a truncation of an infinite series. And this series is called the Kramers-Moyal expansion. But for the kind of problems we look at, it's actually enough to take two first terms. Yes. So let's look at how we get it. Sort of get it for the stochastic differential equation. So this first term is just like the deterministic term, and then the second term is this kind of noise term. And then this is, and kind of the integral of that noise term is called a Wiener process. And the important thing about the Wiener process is that when you take small infinitesimal steps, then you add noise, Gaussian noise, and the variance of that noise scales as kind of the step size. And that looks strange. Why is the step size? Why not the step size squared or something like that? It actually turns out that in order to balance the drift term and the noise term, it has to be like that. And it will also kind of drop out of some of the calculations we do later on when we calculate the elbow for this kind of model. Yes, and how do we then derive the Fokker-Planck equation for the stochastic differential equation? We use what is called Ito's lemma, and that means that we now want to be advanced and look at what stochastic process corresponds to taking a function h of this stochastic process, right? So kind of delta h is then, you know, we change x by a little bit, and then we look at this difference. And then this looks like, okay, we can do a Taylor expansion. So here I've shown just a Taylor expansion up to delta x to third power, and delta x is given by the SDE. So what is special about this? I mean, of course, if you think about it, the best guess is to start by just saying, I mean, you know, this is just, when we look for a stochastic process, we look at something on this form, right? It should be something like some factor times delta t plus some other factor times delta w. And then you can say, why not just truncate this Taylor expansion to first order? No, we cannot do that because there's something special going on here that has to do with the noise and the Wiener process, right? Because you can see that if you take delta w squared, right, then it will be something that is order delta t, right? Because you have kind of fluctuations of dv, they are order square root dt, right? That is kind of the standard deviation of this Wiener process. So that means that actually we have to be careful, and if we have a delta w squared term, we should replace that by delta t, which is like the expectation of this, plus some noise. And it turns out this noise, if you look at it, is kind of order delta t, right? But this term here is order delta delta t square root. So that means that when we take delta t small, then the delta t square root will kind of dominate. But still, this delta t term here will survive. So that means that we can actually kind of look at this expansion and say the terms we need to keep to delta t and delta w looks like this, right? So you can see, compared to the naive application of just keeping the first order term, we get a second order term here, right? Because actually some of the noise actually contributes to the drift, right? So actually noise will go into the drift and have this second order term here. Yes. Now if you play this game of kind of deriving the Fokker-Planck equation again, then it turns out that the Fokker-Planck equation for the SDE looks like this here, down here. So you can see now that actually the drift coefficient from before is simply kind of the drift or kind of term from the SDE, but the diffusion coefficient is kind of the squared kind of noise term here divided by 2, right? And why is this super nice? It's because now if we have an SDE, right, we have, let's say we have trained some neural network, we have some way to learn a neural network based on an SDE, then we can immediately write down how the marginal distribution for that SDE evolves over time. And that will be useful. That will be useful, for example, when we calculate bounds on log likelihoods and similar, as you will see shortly. Yes.
Is the cleanup process in terms of the DT and the noise, is it something we choose or is it something that naturally occurs?
Yes, good question. Yes, I'm not a statistician. So I think the important thing here is that this noise should have variance dt. If we make it any other power, then this will lead to a kind of a trivial SDE where these two terms will not kind of both contribute. Then either one of them will kind of dominate or the other, right? So either it will be like a noise without a drift, or it will be back to the ODE. So it has to be this kind of delta t variance. Yeah.
So if I understand correctly, we keep the second order term of the Taylor expansion because we want to keep all the terms that are order dt. And I think at the first order that makes sense to me, but why dt specifically as opposed to that's what a differential equation.
Yes. I mean, differential equation is something with delta, d's, right? And kind of, in order to have a well-defined stochastic differential equation, we have to have a dt here, and we need to have a dw here with this variance. We need that, right? And now we want to derive a stochastic process for a function of a stochastic process. And that means that essentially it should look the same way, otherwise things will kind of blow up or disappear. And that means that when we do this Taylor expansion, then we should kind of identify all the terms that are scaling with dt or dw. Anything else will kind of disappear, because when we take dt going to 0, dt squared will be much, much smaller than dt. Right now I'm not a mathematician, but you get the drift, yeah.
Make a guess. So for dt, the good property of written process is that the difference in any points can be scaled linearly. If it would be another power, then it would depend on the point where you start. The only way to preserve it on both high scale and low scale.
Exactly. And there's also other processes, for example, Markov jump processes, where the state does not change kind of smoothly, right? So you can also define other processes than this. But this is a nice class that has kind of brought us a lot of nice image generation, for example. Yes, okay, but it turns out actually that this kind of formulation of the model in terms of this particular Fokker-Planck equation with a drift and a diffusion coefficient is not unique, because you can massage the Fokker-Planck equation in order to kind of remove or change the sign of the diffusion term. And you can see that very simply, because now if you look at the diffusion term here, right, it has this second order derivative. So if I take one of these derivatives and move it inside, then I can, I get a term which is d capital X, ddx, this term times p, and then another term which looks like this, where I have used kind of the best trick in the book, take the log derivative, right? So you can see now I have rewritten the diffusion term as a drift term, right? You can see what is a drift term. It's a term where as a first order partial derivative with respect to the stochastic variable, and then something times the marginal, right? So that means that I can actually remove, if I want, the diffusion coefficient term. So if I define this term in here, this plus this, then I can actually write the Fokker-Planck equation like this, where k is a variable I can choose, right? So I can choose, for example, k equal to 0. Maybe I made a mistake here. Let me see now. Oh, I can take k equal to, probably there's a mistake here somewhere. There should be a -1 somewhere. But you can see I can remove this term, and then I can shift the diffusion term into the drift term. And why is that nice? You can see it here, is that actually I can start with kind of the SDE Fokker-Planck equation that looks like this, or I can shift my drift term. I can redefine my drift term so that I remove the drift term and I get back to this ordinary differential equation. I can even change the sign on this diffusion term like this and get a new, here comes a little bit of hand waving, but I can change, when I change this sign, it actually turns out that I get this, what is called the reverse time Fokker-Planck equation, or stochastic differential equation. So that requires a longer proof, and that's this kind of very famous paper by Anderson from 1982, where we define a new Wiener process in this way, and then we actually prove that X and this new Wiener process are independent for times before xt. And why is that nice? It's because if we then run time backwards, then it means that this new Wiener process with a bar over it will be independent going back in time, right? So that means that this is actually another stochastic differential equation just going back in time. But you can see that they are all the same model, right? So that means that we can actually take the same model and we can treat it as an SDE, or we can redefine the drift term and treat it as an ODE, or we can redefine the diffusion coefficient again with a minus sign, and then it's actually an SDE running opposite direction in time. So that's really nice, and this is something that you will also see being used a lot in the diffusion literature. Yes. So that was the hardest part of this presentation. How much time do I have left? Oh, lots of time. Yes. Oh, yes. We started a little bit late. No. We started actually very precise. Yes, okay. Yes, okay, let's just have a look at how you can actually use the Fokker-Planck equation to actually derive likelihoods. Right, so let's look at the ordinary differential equation. I tried to convince you that actually the Fokker-Planck equation for that looks like this. Now I call the drift coefficient just F0. This could be a neural network. Then you can see here we have partial derivatives, and the partial derivative simply means that we kind of ignore that x depends on time, and we only look at the explicit time dependence, right? So that means that if we write the full derivative, then it's the partial derivative plus the time dependence through x. So we can write it like this. And now dx dt is defined by the ODE, and we plug that result in, and then we see that actually two terms cancel, and we get this differential equation for the marginal. And you can see now we have this p here on the other side, so we can divide by that, and then we can use this kind of log derivative trick again, and we then get a simple differential equation for the log marginal distribution, and we can integrate that equation. So now we actually have an expression for calculating the probability at a time 1, for example, in terms of the probability at a time 0, where we, for example, have a simple distribution like this Gaussian distribution, and then we have this integral over time that depends on x of t, and x of t we find that by solving the ODE, right? So we can actually solve two equations. We can solve the ODE, and then we can plug that into this expression and then integrate over time again, and then get the probability at time equals to 1.
It seems that once we go to this diffusion part, and then it's a deterministic equation, so how we interpret the probability distribution shouldn't be like just degenerate and concentrated in the points where actually...
Very good question. We will always assume that there's a distribution at time equal to 0, right? So that means that the stochastic, the uncertainty we have at time 0 kind of propagates, right? So it's true that then, it's true that, at that any point will of course kind of at this density will have a density, and that will kind of propagate forward in time, but it will still be essentially like in this drawing, right? That you can actually kind of move forward in time with it's kind of a distribution moving forward in time.
Okay, so at least if we assume that at time 0 we have like concentrated and moving on. Yes. If we have a delta function at 0, then it will also be a delta function later on. Yes. Yeah.
Maybe it is a silly question, but since this F0 is like taking in some x and t, if we have some deterministic state space equation with which we are defining our time series, so it seems that if we assume that in the prior, that is the x0, we have some normal noise, we just start. So using that state space equation that is a deterministic function, we can have a probability over the time series at any output. Okay. And this can be any function.
Yes. It could be a function that makes kind of white noise into images, for example, essentially, right? So, yeah. Yes. Okay. Yes. Okay. Let me go through this very fast. But you can play the same, okay, just to sketch it, you can play the same game with an SDE. And now our generative model is an SDE, and also our variational distribution is an SDE. And it turns out in order to get well-defined elbow, then actually the noise term for the two cases have to be the same, right? So kind of the two processes have to balance. And you can say, how do we actually calculate an elbow for continuous time? One way you can do it is that you can actually do it and using different kind of theorems from stochastic calculus, but you can also do it simply by going back to kind of what we did in the VDM and discretizing the distribution. So more or less saying that this, when we write down something like this, it defines a conditional distribution with kind of a Gaussian conditional distribution, because this is Gaussian noise, right? And then you can take the kind of prior distribution over your variables, your stochastic variables, and you can also take your variational distribution and write them down as Gaussians, and then you can calculate the elbow. And it has let me go down here and show. It has this kind of diffusion term as before. It has a prior term as before and has a likelihood term as before. And actually, we can write down the diffusion term like this. And you can see, which I think is important, is that it depends on how you define the kind of the drift term in the variational distribution. That's what I call a G, and also the drift term in the generative model. And then we also have to be able to take an expectation over the marginal distribution of the variational distribution. And that sets, of course, if you want to do this efficiently, it sets restrictions on how to choose the variational distribution. And what I will not show, but you can show, is that you can actually define, like if you define your variational distribution as a flow model, you can actually calculate this marginal distribution for any t. So let me show you. Let's take a simple example. If we choose it as a Gaussian, then we can write down so a Gaussian will mean alpha, function of y and t, and variance beta squared. Then we can write down what the drift term becomes for the ODE and what the drift term becomes for the SDE, like this. Right, so that means that we can actually kind of specify our encoder in terms of these quantities, and then kind of our model is then given after this, and then we are of course free. F1 is our generative model. We are free to choose that however we want. But you can see that our drift term in the variational distribution is kind of restricted to something that is kind of linear in the stochastic variable. So it puts restrictions on the drift term. I'm almost done. Also, you can see now that kind of I was worried about this thing that when I looked at this encoder model we had, and then we took the continuous limit, I got the derivatives of my encoder, right? But you can actually see that these derivatives are also here, right? So I have kind of recovered derivatives in the continuous formulation as well. Yes, okay, I'm done. My last slide, can I go through it? Good, okay. Yes, so I tried to convince you that diffusion models are really hierarchical VAEs, and this becomes more apparent when you introduce more advanced encoders than just noising your data. I would say my personal journey is that the continuous formulation is more natural, but there's also a huge learning curve in kind of learning about stochastic processes. But maybe some of you have been in a good school, better than the school, or maybe paid more attention than I did when I was a student, so you know it already, and then I really encourage you to use that model, because I think it's really a powerful tool in contemporary machine learning. There's a lot of things I haven't talked about. I mean, I haven't talked about how to derive the Fokker-Planck equation. I haven't talked about kind of how to derive more mathematical details about the Wiener process and how to derive the Fokker-Planck equation for the SDE. I haven't talked about how to derive this kind of reverse time SDE with this noise that have kind of increments going the other time. I haven't talked about what I just flashed over here, how to go from the marginal distribution to the drift term. These two are not independent. I haven't talked about that you can also use score, you can also use the Fokker-Planck equation for score and flow matching and for stochastic interpolance. But we are writing a paper, and look out on Twitter and archive. It will appear sometime soon. And I will say what I said again at some point. You really learn to love calculus when you do this kind of things. Thank you.
One question, if you use the continuous diffusion approach, has it only tested on some common problem compared to the more stepwise approach that actually improves the whole learning ability, or is it still just architecture?
Yes, very good question. So actually, if you look at the VDM, the actual learning objective we use there is like a stochastic realization of the continuous approach. So in a way, we're already learning with a continuous approach. We're just arriving at it from a kind of finite number of layers angle. So, so I think that already there is kind of, also in the VDM paper, they have an argument saying actually, when you take t to infinity, you get like a higher value for your likelihood, essentially. Then, of course, once you have trained a model and you want to sample from it, the question is how you do that more efficiently. And there maybe you can use an SDE to do it, or maybe you can just discretize space. I think there's a lot of work now, because these models now, we want them to generate fake videos and so on, right? So it's super important that they are efficient. And when you do that, you really want to, you don't want to integrate an SDE, you want to do like three-step generation. So you kind of go back to a discrete formulation again. But I think you can easily combine like learning in a continuous stochastic setting and then generate with a finite number of steps.
Does it make sense to have a look at all this stuff from spectral side, like using Fourier transform, and have a look at how the distributions will behave in spectral space?
When I started my career, I got a job in like a signal processing group, and I was never fond of the Fourier transform. So I'm not the right one to answer that question, but at least, I mean, I think it's very useful to think about this kind of, when you have the generative model, right, that is a big unit, and it's kind of an explicit function of t. Then this unit with a lot of convolutions, it is doing something very similar to kind of a spectral analysis. So I'm pretty sure that if you take the same random noise and feed in kind of close to the prior, you will kind of see smooth things. And if you kind of take the same random noise closer to the data, you'll see more high frequency things coming out. So I think definitely your unit learns to do a lot of Fourier stuff. So I hope that makes you happy, but I'm not a big fan. Sorry.
You mentioned that SDEs, all you need for latent this thing. Is there a reduction in the latent space, or is the latent space still the same dimensionality as the original data, like in the diffusion model?
Yes, it is. Yeah.
There is a reduction in the...
No, it's the same. It's the same, yeah.
Okay. It's just a different, like a continuous perspective to look at.
Yes, exactly. It's like in the neural ODE paper, right, that they say, hey, here's an ordinary differential equation. The right-hand side is a function. That function is a neural network that we learn, right? Okay, thank you, guys.